In this video, we're going to talk about what is a component, and we're going to define a node cut and the connectivity number of a network. Then we'll see some examples, and we'll talk about the connectivity number of trees and cycles, complete graphs, and a graph that we define as the complete graph KS plus the join of M copies of a complete KP. A graph is connected if, given any two vertices, there exists a path from the two vertices, from one vertex to the other, or from one node to the other. So if your graph is not connected, then it's a collection of connected components. You can think of a component, therefore, as a maximal connected subgraph. If you have just one component, then you have a connected graph. A node cut is a set of nodes whose removal increases the number of components. In other words, it disconnects the graph. If you have a connected graph, it may be that when you remove your node cut, then you have many components, or maybe just as few as two. A network can have many different node cut sets. You can think intuitively that if you remove a lot of nodes, you're bound to disconnect the network. So what we're interested in is critical nodes, and we're interested in what is the minimum number of nodes that you could remove from your network to disconnect it. And therefore, the minimum cardinality is what we're interested in among all node cut sets. And this minimum cardinality is the connectivity number of a network. A tree has connectivity number 1. If you draw a tree and you remove any of the nodes on the periphery of degree 1, they do not disconnect the tree. However, any other node will disconnect the tree, and therefore there exists a set of cardinality 1 that will disconnect the graph. So the connectivity number is 1. For a cycle, if you draw the cycle and you remove a node, then you have a path, so it's still connected. You would have to remove 2 non-adjacent nodes to increase the number of components. But since there exists a cut set, or a node cut of cardinality 2, and then its connectivity number is 2. The special case is for a complete graph. For a complete graph, no matter how large your node set is, what remains when you remove that node cut, or rather that set of nodes, the remaining graph is still connected. Therefore, we define the connectivity number of the complete graph to be all but one vertex, or all but one node, and then the single node that is left. Technically, I guess you could say it's no longer connected since it has nothing to connect to, but that's a special case. So for a complete graph on n nodes, the connectivity number is defined to be n-1. We're going to construct a network beginning with the star graph, which is a single vertex of degree m, and its m neighbors are only connected to that single vertex. It's the K1m. Now let's take the central vertex, or the central node that is of degree m, and replace it with a complete graph. Let's replace it with a complete graph of order S. Now, each of the nodes in the complete graph of order S is connected to the M nodes on the periphery. Now, each of the M nodes on the periphery, let's replace them also with a complete graph. Let's say a complete graph of order P. This is the graph that we constructed in the section on the hierarchical networks. We have copies of a complete graph of order P, and they're all connected to the original graph, which is a complete graph of order S. We denote this graph by K sub S, which is the complete graph on S vertices, joined to the M disjoint copies of a KP. What we're interested in now is the connectivity number of this graph. And this graph has S plus M times P nodes. In the picture below, where we have the KS joined to the 4 copies of a complete graph on P vertices, we have a single edge dictated, but what we mean is that every node in the KP is joined to every node in the KS. So if you were to choose one of the KPs together with the KS, the network induced by those two would be complete. What if we remove the S nodes in the KS? In other words, if our node cut is the KS, then we see that it is a node cut because we went from having one connected component to having 4 components. So this is a node cut. Now, is the connectivity number S? We see that we have a node cut set of size S. What we have to do is verify that there is no smaller node cut set, because the connectivity number is the minimum cardinality among all node cuts. If we remove any of the nodes in the periphery and the KP, the remaining network is still connected, even if we remove the entire P vertices in one of the KPs. So I think it becomes obvious that we cannot find a smaller node cut. So if we remove the S vertices, remove the entire KS, we increase the number of components to 4. And if we remove one of the KPs, we still have 1 component. If we remove 2 of the KPs, we still have 1 component. So I think we will agree that this graph has connectivity number S. So we defined what we mean by a component. We defined a node cut and the connectivity number of a network. We saw that the connectivity number of trees is 1 and cycles is 2. The complete graph is a special case that has connectivity n-1 when there are n nodes. And we looked again at the KS plus m copies of a KP. and said it had an activity number equal to S.